Welcome, ladies and gentlemen, to our lecture on the rotation of rigid bodies. So, what do we mean by the term rigid bodies in physics? We mean that as an object rotates, the shape of the object is fixed. So if I have some object here, and I spin it about an axis that's here, the shape of this object doesn't change as it rotates around this axis. We don't have it being deformed. We don't have the sides here oscillating, making weird bumps. It's not suddenly shaped like this, some completely different shape, okay? It stays with this shape here as it spins around this axis here. So something like a spinning basketball would be a good example of this. The basketball is just a round object, and when we spin it, nothing's deformed. As it spins, the shape of the ball isn't changing. It's just sitting there, spinning about some axis. In this class, when we consider spinning objects, we'll be considering them as rigid bodies. So, when something is spinning, let's put an axis here, and let's say we have this disk, and it's spinning around this way. When the object is spinning, if I took any one little piece of mass, this mass would move in a circle around the axis of rotation. Okay? Now, this would be true regardless of the shape of the object. Here I've chosen a disk, but you can imagine even if I had, say, a stick, and it was spinning around an axis that was right here. If I took some little piece of the mass, what this would do is move in a circle. Wow, that is terrible. What this would do is move in a circle around the axis of rotation. Okay? So to describe spinning, we first have to define the axis about which something spins. When we describe spinning about this axis, we pick an axis and we describe the spinning using the right-hand rule. So with the right-hand rule, I take my right hand and I curve my fingers so that it would follow this spinning motion. Okay, so they point in the direction of this spinning. And then if I point my thumb straight out from my hand, it'll point in the direction of the axis. Okay, so in this case, with this thing spinning counterclockwise with my example, and this axis of rotation right here, then the axis is pointing out of the page. If it was spinning this way, the axis would point into the page. So when we're dealing with objects rotating, we generally deal with a changing angle that's expressed in terms of radians. Okay? So if I pick some direction here, then this angle, theta, would describe the rotational position of the object. Now, radians are just a different unit for angles that work out much better in modeling the physical world for many applications, including rotational dynamics. In fact, for many things, only units of radians work for angles. We can't use degrees. Okay? One full circle is 2 pi radians. Okay, that's one full circle. We also know that one full circle is 360 degrees. And so this, right away, will give us a unit conversion. So radians, like degrees, are not what I call a real unit. What I mean by that is that radians are technically unitless, just like degrees were. So your book has a nice breakdown of exactly how we come by radians and why they end up unitless. So I'll leave you to read that there. And you should read that and make sure that you understand it so that you can understand when you use radians in the future what they're telling you. So notice that if I choose some coordinate system, say I say theta equals 0 in this direction, then I can describe the rotational position of the object with this angle theta. So remember when I had a linear system, something was going to move like this, I could pick some coordinate system, say this direction for x hat, pick a point that's 0, and then I could describe the position of the object with the coordinate x. In this case, I'm choosing a direction that's theta equals 0. I have a direction of motion, counterclockwise in this case. And I'm going to describe the rotational position of the object with theta. So we can think of these analogous ideas. X is position. In linear systems. And then when we go to rotational systems, the analog for x is theta, the angular position. And when I have a position and it changes in time, I have a rate of change of that position, right? I have dx dt. And in linear kinematics, we called this velocity. But if theta is the angular position, then I could also have a rate of change of my angular position, right? In fact, if it's spinning, I obviously do have a rate of change of the angular position. And this we call omega. Now, I know that this looks like a W, but it's actually a lowercase Greek letter omega. You may have noticed that I was always using Greek letters for angles as we solve problems up to this point, and this will hold here as well. Normal convention is to use these Greek letters for most of this angular stuff that we're going to talk about, and in that tradition, this thing that looks like a W, it's actually an omega, okay? So, velocity is V in linear systems, and then as we go to rotational systems, it's omega, okay? And omega is angular velocity. But then with straight line motion, remember, I could have a rate of change of my rate of change, right? So dx dt equals v, and dv dt, well, that was acceleration, right? So similarly, I can have this rate of change of my rate of change, and that's d omega dt, and that's equal to alpha. And alpha is the angular acceleration. So when we look at acceleration in a linear system, remember it was a, and when we go to a rotational system, that becomes alpha, the angular acceleration. And these omega and alpha, these are both vectors, okay? Remember, this was a vector. This is also a vector. This is a vector. This is also a vector, okay? And these vectors use this same right-hand rule that we talked about with the axis, okay? And they have a magnitude of whatever the rate of spin is, or whatever the change in the rate of spin is. And they have a direction based on this right-hand rule. So if I have my disk spinning counterclockwise like this, then omega points out of the page, okay? And if it's spinning counterclockwise and then it starts speeding up, that would be a positive acceleration, a positive angular acceleration. And alpha would also point out of the page. Alpha would be increasing the rate of spin. If alpha was slowing down the rate of spin, then effectively alpha would be causing a rate of change of spin that goes in that direction, and alpha would be minus alpha. It would be into the page, okay? Now, notice that we have these linear properties, and for each one we have this analogous angular property. Remember that I started with this equation when we were doing linear kinematics. And from there, I derived a group of equations that we used for kinematics. Well, nothing in those derivations actually relied on these things being linear properties. So if I can replace each of these with the corresponding rotational quantity, all of the same derivations could take place in the same way, and we would have these new equations, okay? So for example, in this one, theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And this would be a kinematic equation for rotation. These equations, these kinematic equations derived in this way, they're all true in the physical world. And just like these linear equations were useful for objects with constant acceleration, these angular equations are true for objects with constant angular acceleration. And this gives us a whole new tool. Now we have a tool of angular kinematics, okay? And in fact, this establishes a trend in the way that rotational physics works. If we have some principle that we've established in linear motion, okay, like this kinematic equation, we can replace each piece with its analogous rotational property, and it turns out that that will produce a rotational physical principle, okay? Now, replacing them isn't how we come up with this stuff, but it does turn out that if we replace each piece with the correct analogous rotational physical principle, then we have new physical principles, okay? So remember, by taking the derivative, I showed that v equals v naught plus at. Well, then this equation becomes omega equals omega naught plus alpha t. And this one is true in the physical world, okay? And this works for all kinds of things, not just for these kinematic equations. So for example, remember we had momentum equals mv. If we replace each of these pieces with the correct rotational quantity, or angular quantity, then we have a new thing called angular momentum. And angular momentum is a real quantity in the physical world, and conservation of angular momentum, just like we had conservation of momentum, is another true property in the physical world. So now, I told you that we can get all these physical principles for rotational motion by replacing linear properties with rotational properties. And I even mentioned that there's such a thing as angular momentum. And it's also conserved. So we know we have linear momentum, and we know that that's equal to mv. So I replace something, p, with something that represents angular momentum. We usually use L, capital L, for angular momentum, okay? And then I replace v with omega, right? That's the angular velocity. And then I replace mass with what exactly? What's angular mass? So mass is a quantity that dictates your linear inertia, how hard it is to change your linear velocity, okay? To describe your angular inertia, how hard it is to change your angular velocity, we have something called moment of inertia, and that's usually denoted using a capital I. So let's look at some rotating object. For any little piece of mass that makes up this object, this piece of mass moves in a circle around the axis of rotation, right? That's something we already mentioned. And this would be true regardless of the shape of the object or the axis of rotation. So then, as an aside, that gives us our first little insight here. Using uniform circular motion for any moment in time, we have some angular velocity, omega, and that means that for this moment in time, we have some tangential velocity, v, okay? So if we had, say, a little piece of mass out here on the edge of the object, it would have this tangential velocity v, right? Now, the arc length covered in some little tiny piece of time, ds, in some little piece of time, dt, well, that would be equal to r times the change, the little tiny change in the angle in that little piece of time, okay? And this ds dt becomes v, this tangential velocity, if we make the piece of time really, really tiny. And then we have r, and d theta dt, of course, is omega. And this is a basic physical principle that you should remember for future use. This also only works with radians. Okay? Radians allow us to find arc lengths like this. Degrees do not. So don't go plugging degrees into an equation like s equals r theta. Okay? If you plug degrees in for this angle, it doesn't work. You have to plug in radians for this angle. And again, if you go to your book and read how we derive radians, then you'll understand why this is the case. Okay? But now, notice that if I was spinning this object at some fixed omega, each little piece of mass would have a different kinetic energy based on its linear speed. Okay? Notice that its linear speed is r omega. We have a rigid body, so omega is the same for every little piece. So imagine I had a little piece here. Well, for this piece out here, r is this long piece, right? For this piece here, r is this little short distance, right? And omega is the same for both, because when we have a rigid body, omega is the same for every piece of the body. Okay? For it to not change shape, they all have to have the same angular velocity. So I have a different speed for every little piece. And that means I'm going to have a different kinetic energy for every little piece. That different kinetic energy is tied both to the differing speeds of the little pieces and to the differing rotational inertia of each piece. So if I added up the rotational inertia of each little piece, that would give me the rotational inertia of the whole object, the moment of inertia. And notice that I could write the kinetic energy for any one little piece as 1/2 mv squared, right? And we know that v equals r omega, so this is 1/2 m r squared omega squared. And remember that I was telling you that we can get angular physical principles by replacing each piece, each linear piece, with an angular analog, okay? So omega is the analogous angular property of velocity, right? So if that's the case, then what I have here is a half is just a half, right? It's the same in angular terms as it is in linear terms. And so I have 1/2 m v squared in linear terms, and I have 1/2, and then I have this m r squared omega squared in rotational terms. If these two are analogous, and the halves, of course, are analogous, then that means that my mass goes to mr squared in angular terms, okay? This is the angular inertia for this little piece. And again, if I add up all the little pieces, then I'll have the angular inertia of the whole object, which is what we call moment of inertia. So I equals the sum of all the little masses and their distance from the axis of rotation, squared. Now, notice that this means that the moment of inertia depends on the object's mass and it depends on its shape, right? The little r squared of each piece, that's going to define the shape of the object, right? But it also depends on what axis of rotation we choose. So the same object can have a different moment of inertia when we pick a different axis of rotation, okay? If my axis of rotation for this disk was out here, okay, say I connected something right here and then I spun the whole disk around this point, then this little mass, its r from the axis of rotation, it wouldn't be this distance, right? This little r. It would be this distance, okay? It would be the whole diameter of the disk instead of just the radius of the disk. So our moment of inertia is going to depend on the shape of the object, the mass of the object, and the location and direction of the axis of rotation. So now let's go to our infinitesimals, which by now you know means that I'm headed for an integral, right? So let's say we have some infinitesimal little mass, dm. Then adding up all of the r squared dm's would create the whole object and give me the moment of inertia for the whole object, okay? Now, since these are little infinitesimal pieces, adding them up, when I make them as small as possible, when I take them down to their tiniest size, it would mean doing the integral r squared dm, right? And that's going to give me the moment of inertia of a whole object. And this r squared, of course, is going to depend on the shape of the object and the axis of rotation, right? And the dm, well, that is a little infinitesimal piece of mass. And that's going to depend on the density, rho, times the volume of that little piece of mass, okay? And density is actually mass per unit volume. So for our infinitesimal thing, it's dm over dv, okay? That's where this rho dv came for dm. So now if we can assume that rho here, the density of the object, is constant, okay, if we have something of uniform density, like a billiard ball or something like that, then we can pull it outside of the integral, put it out here, and we have r squared dv, okay? Now, this dv is going to depend on the integral that we're doing, and we'll have to choose geometry that allows us to add up all of the mass of an object, okay, based on the axis of rotation and what this r squared is, okay? This usually requires some kind of clever thinking to put together the whole mass of the object, okay? So for example, for a sphere, we think about having little coins, and we stack up coins of different heights like this, okay? And this looks really coarse, but you can imagine if I make my coins thinner and thinner until they have some infinitesimal little thickness, then I can actually create a sphere by stacking up these coins, okay? And so we do that kind of a calculation if we're going to try to find this moment of inertia for something like a sphere, okay? So that's one example of how we might define this r and this dv in such a way that allows us to perform this integral and calculate the moment of inertia, okay? Now, these things can take some time to explain when we do a specific one. So in the interest of time, I'm going to skip deriving a moment of inertia right now. But I will expect you to know how to do it if you need to do it for a problem. So make sure you carefully read section 9.6 in your book, okay? Your book has a couple of really well done examples in this section, and in particular, the one with the sphere is really, really nice. They use the little stack of coins thing to find the moment of inertia of the sphere. And basically, I think that my ability to draw it on this page and explain it is going to take a lot of time, and my ability to draw it might actually just muddy the conceptual idea here. So I'd rather you read it out of your book with their really nice figures, and make sure that you do the examples yourself, okay? Work through the math yourself, write down everything, understand what every little piece is, and make sure that you can do it yourself. Because if I give you some object that you need to find a moment of inertia for, I'll expect you to be able to do it. So for common shapes like a disc or a sphere or maybe a box or a plate of some kind, or maybe you have a really thin little rod. For those kinds of common shapes, we generally keep tables for the moments of inertia because we do the integral to find the moment of inertia once, and then we can just look it up for something that can be approximated as that same shape later. Okay? As a general rule, for objects with some kind of nice angular symmetry, the moment of inertia is going to come out as some number c times m r squared. Okay? So, for example, if we had a sphere here with the axis of rotation going through the center of the sphere here, and then rotating around that like this, then this moment of inertia for a sphere of uniform density rotating around an axis that goes through its center of mass is 2/5 m r squared, where r is the radius of the sphere. Okay? For something like a stick, spinning about an axis that goes through its middle like this, okay, spinning around like this, with a length L, then for this one, I equals 1/12 m L squared. Okay? And we keep tables for moments of inertia for all kinds of basic objects. And generally, it just means looking in a table for what this number is going to be. Okay? So, for a lot of objects, we'll just look up the moment of inertia. And I'll give you guys a link to a list of a table like this, and you'll be able to look up those ones as well. So we won't waste time calculating the moment of inertia for simple objects for every problem that we do. There will generally be something that you can look up like this, and we'll use that. So this brings us to something called the parallel axis theorem. And we can use the parallel axis theorem to find the moment of inertia for an object when it's rotating about an axis that doesn't go through its center of mass. Okay? So objects will normally rotate around their center of mass when they aren't being interfered with. But sometimes we have things that are interfering with objects and forcing them to rotate around a different axis. For the parallel axis theorem, let's consider just a rod for a moment, or a stick. So let's say we have some solid rod of uniform density here. We can find the moment of inertia for an axis that goes through here. Okay? And that one I told you earlier is 1/12 m L squared, where L is the length of the rod. Okay? And the center of mass, of course, for a rod of uniform density is going to be right through the middle here. Okay? So that's our moment of inertia for the center of mass of this rod. But if we were to attach one end of this rod to something and then spin the whole rod around this, okay? Then we would have a different moment of inertia. And the parallel axis theorem allows us to calculate this new moment of inertia without redoing the whole integral and all of that. okay? So if we have these two axes, the parallel axis theorem first requires that these two axes of rotation be parallel to each other. That is, that they're pointing in the same direction, okay? So if I have some axis of rotation over here on the left that I'm concerned with, the first thing I need to do for the parallel axis theorem is know what the moment of inertia would be if I was spinning the object around its center of mass, or around an axis in the same direction that went through its center of mass. Okay, that would be this axis over here on the right. Okay, this one's pointing in the same direction as the one on the left, but it goes through the center of mass of the object instead of the one end of the object or some other place. Okay? Then what the parallel axis theorem tells us is that when we have these two parallel axes, for spinning around this axis, the moment of inertia, I of the parallel axis, is equal to the moment of inertia of the center of mass axis plus the mass of the object times a distance d squared. And the distance is this distance between the two axes. This is d. Okay? And that's it. Anytime I can take the center of mass and draw an axis parallel to the one that I care about through the center of mass, and I know that moment of inertia, I can find the new one with this simple little trick. Okay? So this is the parallel axis theorem. So now let's consider our example of the stick, okay? If I want to find IP, so the moment of inertia when I spin about this axis right here, that's equal to ICM, which is the moment when I spin around this axis through this parallel axis through the center of mass, plus the mass of the stick times d squared, okay? Now I told you that a stick spinning around this axis through the center of mass, it has a moment of inertia of 1/12 m L squared, where L is the length of the stick, okay? And then that's plus m, and then d, notice, is just half the length of the stick, okay? So 1/2 L is equal to d, and then that's squared. This means that IP equals, this half inside the square is going to become 1/4, right? So it's 3/12. So we have 4/12 m L squared, which is equal to 1/3 m L squared. And this is an agreement if we had done the integral using this axis over here. Okay? So this parallel axis theorem is a basic physical principle that you should know, and it works regardless of our choice of object or axis, okay? It just requires that we know what the axis, what the moment of inertia would be when we spin through this parallel axis that goes through the center of mass, okay? So now let's imagine that I have a sphere and I connect it to something here, and I'm going to spin it about an axis like this, okay? So if that was the case, let's say the sphere is uniform density. So let's say it's like a billiard ball and I've attached it to a stick, and then I'm going to spin the stick around. What's the moment of inertia of the billiard ball when it's spinning around attached to something on the edge of it like this, instead of spinning around through the center? Well, remember that I told you earlier that for this axis through the center of mass, ICM for a uniform density sphere is 2/5 m r squared. Okay? So then the parallel axis theorem says that IP equals ICM plus the mass of the sphere times d squared, where d is this distance between the two axes, okay? So then ICM is 2/5 mr squared, right? And that's plus m, and then what's d? Well, d in this case is just the radius of the circle, right? R. Because I'm attaching it right to the edge of the circle, or the sphere out here. The radius of the sphere, not the radius of the circle. So the radius of the sphere out here. So then I can replace d directly with r, that's squared, and this thing is equal to 7/5 m r squared. And just like that, I have the moment of inertia for spinning about this axis that is tangential to the sphere out here on the edge instead of the one through the center here. Okay? So now we know as we go to rotational physics, we take these linear properties, we replace them with an analogous angular property, and then we can deduce the angular physics. Okay? So for position, we went from x to theta, right? And then we know for velocity, we went to angular velocity. And acceleration went to angular acceleration. Okay? Now we just learned that mass, the inertia of an object, goes to the rotational analog for inertia, which is the moment of inertia. Okay? And now if we wanted to write Newton's second law, right, this is one of our most fundamental pieces of physics knowledge that we have right now, right? So if we wanted to write that for rotational physics, we would say this is equal to I, right? The mass goes to I, the A goes to alpha, the angular acceleration, and this force, the angular equivalent of force, or the angular analog, not equivalent, the angular analog of force, is torque, which we write with this uppercase Greek tau, okay? And torque, like all of our other angular quantities, is specific to the axis of rotation, okay? So now imagine that I have a bolt here, okay? And if I want to untwist it from an object, in other words, I want to spin it about an axis that goes through its center, then much like with linear motion, where objects don't change their linear velocity unless there's a net force acting on them, in angular motion, objects don't change their angular velocity unless there's a net torque acting on them. Okay? So to unscrew this bolt, I might put a wrench on it, right? And I have a wrench that goes out like this, okay? Now if I take this wrench and I push on it this way, right? So I have the force of a push, pushing in like this, so that I'm applying a force on the bolt that goes like this, then nothing happens, right? We know that that won't unscrew the bolt. So when I put the wrench on the bolt, what I do is I grab it out here and I push it this way, right? And we know that if I do that, the wrench will turn around this way and unscrew the bolt, okay? By pushing the wrench out here and pushing it perpendicular to the direction of the bolt, I apply a torque, okay? And the torque changes the angular velocity of the bolt, making it spin. So torque ends up being our angular analog for force, okay? And the quantity torque is equal to R cross F. So it's a function of both the force applied and the distance from the axis of rotation. Okay, remember this is an axis of rotation pointing out of the page, and this R in this case would be this right here, R. And it gets bigger proportional to each of these quantities. So now we finally have the reason that I've made you calculate a cross product on every homework so far. Okay? This is where it comes in. Torque is a cross product. So we know that the magnitude of torque then is equal to the magnitude of this cross product, which we know is RF sine theta, right? Where theta is the angle between the two quantities, so theta, like that. And we know that the direction follows the right-hand rule. So R, I have this arrow from something else I was talking about. That's not good. So R, of course, points from the axis of rotation out to where the force is applied, okay? So R is pointing this way, okay? So then if we use the right-hand rule, R cross F points out of the page. And remember, when we're talking about rotations, the right-hand rule tells us that out of the page means counterclockwise, okay? If I turned F around so that it pointed this way, then the right-hand rule would show me that R cross F points into the page, and what I would get is a rotation that goes this way, okay? And if you just look at my drawing of the wrench, that makes sense, right? That's how a wrench works. If I push this outside edge up, I'll get this counterclockwise rotation. If I push this outside end of the wrench down, I'll get a clockwise rotation, okay? And note here that torque is R cross F and not F cross R, okay? F cross R will give the wrong direction because, of course, F cross R is equal to minus R cross F, okay? So when we have a cross product like this, the order does matter, okay? I can't just flip the order around like I can with scalar multiplication, okay? So this new tool that we have, torque, allows us to write an angular version of Newton's second law. And of course, once we had Newton's second law in linear physics, we could start to consider all kinds of physical systems, right? And we derived all kinds of things from Newton's second law. The same is true here. Now we have, with torque, all of the tools that we need to discuss Newton's laws in terms of angular motion instead of linear motion. So the bolt on this axis through the middle here spins on the axis with angular acceleration that is a vector in the same direction as the torque vector, okay, out of the page as I've drawn it here. We define that direction using the right-hand rule, and we end up with this, the sum, oh, I didn't put the sum in here. The net torque, the sum of the torques on an object, is equal to the moment of inertia times the angular acceleration, okay? Our angular version of Newton's second law. So with this addition of torque to our toolbox, we now have everything we need to understand the analogous rotational motion for all of kinematics and for Newton's laws. So everything that we covered in the first two tests. We'll take the next step further in the class and talk about angular energy and angular momentum as we go forward.